Chapter 7, Lecture 5, Reversible Steady Flow Work. So in this section of the book, we're going to begin to look at reversible steady flow work. The work done during a process depends on the path followed as well as on the properties at the end states. Recall that a reversible moving boundary work associated with closed systems is expressed in terms of the fluid properties. We can express that as the following integral. It's the integral of PdV from state 1 to state 2. Using the TDS relations, we can express the work associated with steady flow devices in terms of fluid properties, which are often easier to calculate. We can rewrite that as follows. This relation gives the reversible work output associated with an internally reversible process and a steady flow device. Now this becomes really important in the last section when we actually start looking at turbines, nozzles, compressors, and other devices, and how we can actually use them as devices to do the work we want to do. The above relation will give a negative result when work is done on the system. To avoid the negative sign, the equation can be written for work input to the steady flow devices, such as compressors or pumps, as follows. One needs to know the specific volume as a function of pressure for the given process to perform the integration. When the working fluid is incompressible, the specific volume remains constant during the process and can be taken outside the integral. The equation then simplifies to the following form. For a steady flow of a liquid through a device that involves no work interactions, such as a nozzle or a pipe, the work term is 0, and the equation can be expressed as follows. This is known as the Bernoulli equation in fluid mechanics. We will work with this extensively in the fluid mechanics course. Let's take a look at this using an example 712, compressing a substance in liquid versus gas phases. Determine the compressor work input required to compress steam isentropically from 100 kilopascals to 1 million pascals, assuming the steam exists as A, a saturated liquid, and B, a saturated vapor at the inlet state. So here shows a picture of the pump. We need to compress a liquid or a compressor to compress a vapor. You can see both of them are coming in at 100 kilopascals and exiting at 1 million pascals. The diagram on the left shows the TDS diagram of the process. So for part A, we're starting down here on the left. We're going from 1 to 2. And then on for part B, we're up on the vapor state. So we're over here going from 1 to 2. So let's look at state A first as a saturated liquid. So we're going to use it as a pump. We're going to let a pump do the compressing. So in this case, the steam is saturated liquid initially and has a specific volume that we can look up in table A5. It's V sub F at 100 kilopascals. This remains constant in the process, as you can see, as he states. Thus, we can take V outside the integral and do the calculation. We get 0.94 kilojoules per kilogram. So that's how much work it takes to compress it from 1 to 2. Now, for part B, let's take a look at how a compressor would work for it. This time, the steam is saturated vapor initially, as we can see from where we start on the Tds diagram, and remains a vapor through the entire process up to point 2. So the specific volume of the gas changes considerably during the compression process. We need to know how V varies with P to perform the integration. In general, this is not readily available, but for an isentropic process, it's easy to obtain from the second TDS relation by setting ds equal to 0, which in this case it is. If you notice here, entropy stays constant. It's an isentropic process. So if we go back to this equation and we set ds equal to 0 here, well, obviously this left-hand side is 0, so we just get VdP is equal to dH. So we can substitute that in the integral. So this essentially just becomes the change in enthalpy from state 2 to state 1. So we can look those values up. At state 1, we can look up in table A5, we can determine the entropy S, and the enthalpy, H. And from state 2, remember the entropy is constant, but we can read off the new enthalpy. Then we can calculate the work necessary to go from 1 to 2. This is the difference between the enthalpy, 519.5 kilojoules per kilogram. So here we observe that compressing the steam in a vapor form would require over 500 times more work than compressing in a liquid form between the same pressure limits.